Welcome, dear listener, to Dreamtime Science, a haven of peace beneath the vast, sleeping sky. Picture yourself in a small, cozy alcove, cushions gently stacked around you, dim candles casting flickering shadows on the old wooden shelves nearby. The air is still, and outside the stars watch quietly like ancient guardians. We are grateful you've chosen to step into this hush with us. If you feel moved by the gentle tales we share, a quiet like or subscription would be a welcome echo, and please do whisper in the comments where your quiet place may be. Now, before we begin, adjust the softness beneath your head. Close your eyes if you wish, and fill your lungs with a deep, slow breath. Together we will embark on a tender voyage where science takes on the silky cloak of night, inviting your thoughts to rest and your imagination to soar gently toward sleep. Shall we begin? Tonight we glide very slowly, very gently through the starlit vastness, where distant worlds, exoplanets, dance in the tender embrace of their suns. Among these cosmic neighbors lies the Goldilocks zone, a whispered promise of just right warmth and mystery, inviting our curious hearts to wonder softly. Let's drift together, keeping a safe, pillow-soft distance as we explore these celestial havens bathed in twilight's hush. A soft tap of the like button or a whispered subscription tells me these calming discoveries resonate with you. What aspect of science brings you the most wonder? Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. Somewhere in the quiet of your room, the world outside softens into shadows, and your mind, untethered from the day's demands, begins to drift. It is here, in this tranquil twilight, that we embark on a journey far beyond the familiar boundaries of home, out past the blue and green marble of earth, slipping between the distant lanterns of stars into the vast, bubbling porridge of the universe. Let us begin with a story that is older than the galaxies, yet as familiar as a bedtime fable, the tale of Goldilocks and the 3 bears. You may recall how a curious child wanders into a cottage in the woods and samples 3 bowls of porridge, one too hot, one too cold, and one just right. This simple theme of things being not quite right or just right has followed humanity from the fireside into the laboratories and observatories of modern science. It now lingers, rather surprisingly, in the language astronomers use when they search for life beyond our world. For as long as we have looked up at the night sky, we have wondered what might be out there. In the 1960s, as the golden age of science fiction blossomed, imaginations soared aboard the starship Enterprise and through the twin suns of Tatooine. Star Trek and Star Wars opened the gates to infinite diversity and possibility. Captain Kirk would stride confidently onto the surface of an alien world, the air breathable, the ground familiar beneath his boots. Luke Skywalker might gaze longingly at sunset, dreaming of distant adventures. These universes, shaped by storytellers, offered planets as diverse as deserts, ice fields, and jungle moons, each teeming somehow with life. But how many of those worlds could truly exist, and what would it take for one to cradle life as our Earth does? To answer these questions, we must first leave the comforting orbit of our own sun and learn to see the cosmos as astronomers see it, not as a cold emptiness, but as a kind of celestial kitchen where stars simmer and planets form in the bubbling, frothy mixture of gas and dust. This is the universe's porridge, an endless recipe combining hydrogen and helium in star forges, seasoning with heavier elements, stirring in gravity's patient hand. Sometimes, when the ingredients and the conditions align, planets are born. Some are giants of gas and storm, others rocky and small, and a few, perhaps, are just right. But what does just right mean truly? In science, the Goldilocks zone is not a cottage in the woods, but a mathematical shell surrounding a star. It is technically called the circumstellar habitable zone. Here, a planet might orbit at a distance where temperatures are neither too hot nor too cold, but just right for liquid water to persist on its surface, a key ingredient, at least for life as we know it. Earth, of course, is the archetype. We celebrate its delicate balance, not scorched like Mercury, nor frozen solid like the moons of Neptune. But the more we learn, the more we see that the universe's porridge comes in infinite flavors. The Goldilocks paradigm, simple and comforting, is not always so tidy. For centuries, astronomers could only guess at what lay beyond our solar system. The stars were too distant, the planets, if they existed, too faint to glimpse. And so, Earth was the only example we had, the only bowl of porridge we could taste. Mars and Venus, our close neighbors, both failed the Goldilocks test in different ways. Venus, shrouded in acidic clouds and baked by a runaway greenhouse effect, is a world of stifling heat. Mars, on the other hand, is a frigid desert, its thin atmosphere unable to hold warmth or water for long. It was easy, then, to imagine that life, if it existed at all, required a planet like ours, just the right distance from its sun, just the right size, just the right kind of air. Anything else was too hot, too cold, too strange. But time and technology have a way of revealing the universe's deeper complexity. In 1992, astronomers made a discovery that would forever change our sense of place. They found, orbiting a distant pulsar, a dead spinning corpse of a star, not one but two planets. These were the first true exoplanets, worlds outside our solar system, circling other suns. The floodgates opened. With techniques as delicate as a spider's web, astronomers began to tease out the subtle wobbles and dimmings in starlight that betray the presence of a planet. The Kepler Space Telescope, launched in 2009, turned its gaze on a patch of sky and watched patiently as stars flickered, each flicker a sign of a world passing in front of its sun. What they found was more astonishing than any fiction. The universe, it turns out, is brimming with planets. Billions upon billions. Some are gas giants that huddle close to their stars, so-called hot Jupiters, their atmospheres boiling with heat and wind. Others are rocky and small, like Earth or Mars. There are planets that orbit in dizzying days, so close to their sun that a year is over in less than a week. Some circle twin stars, like the famous Tatooine. Others float alone, ejected from their systems, wandering the dark between suns. And among this dazzling menagerie, astronomers began to search for planets in the Goldilocks zone. At first, these were rare. The data was noisy, the signals faint, but as the years passed, the list grew. Kepler 186f, a rocky world orbiting a cool red star, was announced with excitement. It was about the size of Earth, and it lay within its star's habitable zone. Proxima Centauri b, circling the nearest star to our Sun, is another tantalizing candidate. Scientists now estimate that in our galaxy alone there are likely hundreds of millions of planets that might be just right for life. But as we peer deeper into the universe's kitchen, the simplicity of the Goldilocks story begins to dissolve. The more exoplanets we discover, the more we realize how many recipes the cosmos is cooking at once. The Goldilocks zone, defined only by distance from a star, is a helpful start, but it is no guarantee of habitability. Planets may have thick, choking atmospheres, or none at all. Their surfaces may be blanketed in ice, or battered by cosmic radiation. Some may be tidally locked, presenting one face always to their sun, while the other lies in perpetual night. And so scientists have begun to ask, is life limited to planets like Earth, warmed gently by a sun, with liquid water and a protective sky? Or could it flourish in places far stranger, in forms we have not yet imagined? To answer this, we need only look back to our own solar system, where surprises await in the cold and the dark. On Jupiter's moon, Europa, beneath a crust of ice, there is evidence of a vast salty ocean, warmed not by sunlight, but by tidal forces, the flexing and squeezing of the moon as it orbits its giant planet. On Saturn's moon, Enceladus, geysers of water vapor erupt from cracks in the ice, hinting at another hidden sea. Even on Earth, life thrives in the most unlikely places, in the scalding vents at the bottom of the ocean, where sunlight never reaches, in acidic pools and frozen wastes, in rocks deep beneath the surface. Each discovery teaches us that life, once it begins, is tenacious. It adapts, endures, transforms. The lesson, then, is that the universe's porridge is not one recipe, but many, each bowl different, each possibility waiting to be tasted. The Goldilocks zone is not a hard boundary, but a suggestion. It is a starting point, a place to search, but not the only place to dream. Science fiction, with its endless parade of alien worlds, has always hinted at this richness. In the Star Trek universe, the crew encounters silicon-based life, energy beings, and creatures that dwell in the clouds of gas giants. In Star Wars, life flourishes on planets of every conceivable climate, from the frozen spires of Hoth to the forests of Endor. These stories are not bound by the constraints of real chemistry or planetary physics, but they capture a deeper truth, that life, in the imagination at least, is boundless. Yet reality is catching up to fiction. With each new exoplanet catalogued, each spectrum analyzed, astronomers expand the boundaries of what is possible. We have found planets where rain falls not as water, but as molten glass, whipped sideways by winds faster than sound. We have seen worlds with skies stained red by the light of their cool suns, and surfaces scorched by ultraviolet radiation. We have glimpsed the shadows of planets that orbit dead stars, their histories written in the rhythms of cosmic catastrophe. And in all of this, one myth begins to unravel. The myth that life can only exist on planets exactly like our own. The universe, it seems, is more inventive, more patient, and more surprising than we dared hope. There may be forms of life that do not need sunlight, or liquid water, or even a solid surface to cling to. There may be biochemistries as yet undreamed of, living in the clouds of sulphurous worlds, or deep within the metallic hearts of icy moons. So as you drift gently through the universe's porridge, let your mind linger on the possibilities. Every star in the night sky may shelter worlds unknown, every planet a different flavor, a different chance for life to emerge. The Goldilocks tale is only the beginning of our curiosity, not its end. It's somewhere perhaps on a planet orbiting a faint red sun, life stirs in the twilight, eyes opening to a sky unlike any we have ever seen. Or perhaps in the darkness between stars, a lonely world carries its own warmth, its own recipe for existence. The search is only just beginning, and the universe's porridge simmers on, rich and strange, waiting for us to taste what comes next. Beyond the Goldilocks zone, beyond the tidy boundaries of our old stories, lies a cosmos of endless invention. As the night deepens and your thoughts float free, let them wander among the stars, through the kitchens of creation, where every bowl of porridge is different, and every world is a new and wondrous possibility. The next step in our journey awaits, a step into the unknown, guided by curiosity and the gentle pull of distant suns. Out beyond the familiar embrace of our solar system, where the sun's light fades into the deep velvet of interstellar night, lies a boundless diversity of worlds. Each one is a silent wanderer, circling its own star in the great cosmic waltz. These are the exoplanets, planets beyond our sun, whose existence, once only imagined in the dreams of astronomers and poets, now numbers in the thousands, their discovery flickering through the telescopes and sensors of our age. Each exoplanet is a testament to cosmic inventiveness, a singular expression of the universe's capacity to sculpt matter into endlessly varied forms. Yet in our search for life, we are drawn time and again to a particular notion, the Goldilocks zone. This modest phrase, borrowed from a children's tale, speaks of a region around a star where conditions are just right, not too hot, not too cold, for liquid water to endure upon a planet's surface. It is a practical dream, born of our own needs and biology, for on Earth, where water flows, life flourishes. And so, as we scan the heavens, we measure star by star, planet by planet, asking, is it in the habitable zone? Is it just the right distance for warmth, for oceans, for the possibility of something living and breathing beneath an alien sky? But what does it truly mean to be just right? Is this thin circumstellar ribbon a guarantee, a promise that wherever the invisible hand of temperature draws this line, life will spring forth as it has here on Earth? Or is the Goldilocks zone but one ingredient in a far more intricate recipe, a necessary condition perhaps, but far fra? Sufficient on its own? Let us drift closer into the delicate complexities that shape the fate of worlds. The Goldilocks zone is a concept both elegant and deceivingly simple. Imagine a star, and then, like the rings of a tree, a band encircling it. Too close, and a planet is scorched, its oceans, if they ever existed, boiled away, its skies thick with steam or stripped bare by relentless radiation. Too far, and perpetual winter reigns. Whatever water there may have been is locked as ice, the air itself perhaps frozen onto the ground. Between these extremes lies a temperate band, a region where, given the right atmospheric pressure, water can persist as a liquid, a solvent for life, a medium for chemistry. Yet, as we've come to learn, this zone is more of a guideline than a law. The width and position of the Goldilocks zone depend intimately on the star itself, its size, its age, its luminosity, its temperament. A small red dwarf star offers a zone so close that a planet must orbit tightly, often leading to tidal locking, one face always turned toward the star, the other plunged forever into darkness. Around a giant hot star, the zone is a broad, distant band, but such stars burn out in a few million years, perhaps too brief a window for life to gain traction. And then there's the matter of planetary atmosphere. A world with a thick greenhouse gas-rich envelope, a blanket of carbon dioxide, say, or methane, can trap heat, keeping its surface warm even at the outer edges of the habitable zone. Conversely, a thin or absent atmosphere offers little protection, and a planet may freeze despite being theoretically just right. The Goldilocks zone thus shifts and flexes, a moving target, sensitive to the unique character of every planet and every star. Our own Venus and Mars are cautionary tales. Both lie near the edges of our Sun's habitable zone, and both have histories that, in some ways, mirror our own Earth. Venus, a near twin in size and composition, is ensnared by a runaway greenhouse effect. Its clouds, sulfuric acid, churning in an atmosphere nearly 100 times denser than ours, trap heat so effectively that the surface blisters at over 460 degrees Celsius, hot enough to melt lead. Any water it once had is long gone, lost to space or bound in minerals. Mars, smaller and farther out, once boasted rivers and lakes, perhaps even an ocean, but its feeble gravity could not hold on to a thick atmosphere, and so it cooled and dried, becoming a desolate, frozen desert. Here, then, is the first lesson in cosmic complexity. Location alone is not destiny. A planet's potential is shaped by a symphony of factors: distance, atmosphere, composition, magnetic field, internal heat, and the tumultuous history of impacts and volcanism that shape its surface and sky. The Goldilocks zone is an invitation, not a guarantee. As astronomers peer deeper into the galaxy, their gaze sharpened by instruments like Kepler and TESS, the astonishing diversity of exoplanets comes into focus. Some are rocky, like Earth and Mars, but others are super-Earths, several times our planet's mass, with gravity that would make every step a labor. There are mini-Neptunes, shrouded in thick layers of hydrogen and helium, their surfaces, if they exist, hidden beneath crushing pressures and alien clouds. Some worlds orbit in dizzying proximity to their stars, completing a year in mere days, their skies ablaze with perpetual daylight. Others drift on the outskirts, locked in endless twilight. Consider the water worlds, planets with vast, deep oceans, perhaps hundreds of kilometers thick, their floors cloaked in perpetual darkness and ice. On such worlds, any life that exists would never see the sky, living instead in the strange, pressurized depths. Or the desert planets, where water is scarce, and life, if it endures, must cling to isolated oases, eking out an existence in the shadows of rocks. Then there are the rogue planets, torn from their stars by gravitational chaos, wandering the galaxy alone. Though they drift in cold and darkness, some may harbor subsurface oceans, warmed by the decay of radioactive elements or the residual heat of formation. Even such lonely frozen worlds cannot be entirely dismissed as sterile. The chemistry of life as we know it is intricate and demanding. Carbon, with its unrivaled ability to form complex, stable molecules, is the backbone. Water, a remarkable solvent, facilitates the dance of atoms and energy. But the presence of these elements and compounds depends on the earlier history of the stellar nursery, the supernovae that seed clouds with heavy elements, the accretion disk that coalesces into planets, the bombardment of comets and asteroids that deliver water and organic molecules. Some stars, especially the older, metal-poor ones, may host planets with little carbon or with atmospheres rich in ammonia or methane, giving rise to chemistries quite unlike our own. On certain worlds, the seas might be of ethane or methane, as on Saturn's moon Titan, raising the tantalizing possibility of life as we do not know it. The planetary magnetic field, often overlooked, is an unseen guardian. On Earth, our field shields us from the solar wind, deflecting charged particles that would otherwise strip away the atmosphere and bathe the surface in sterilizing radiation. Mars, with only a weak remnant field, could not protect its air. Venus, with none, was left at the mercy of the sun. A world's core and its rotation, its deep, invisible machinery, may therefore spell the difference between a living planet and a barren one. The interplay of plate tectonics, too, is profound. On Earth, The restless dance of continents recycles carbon, stabilizes the climate, and builds mountains and ocean basins. Without this geologic engine, a planet's surface may stagnate, its climate veer toward extremes. Yet, the presence of plate tectonics depends on the size, composition, and heat flow of the planet, and perhaps upon the presence of water itself, which lubricates the moving plates. Even the presence of a large moon may be significant. Our own moon, born of a colossal impact in the planet's youth, steadies Earth's tilt, lending a measure of regularity to the seasons. Without it, our axis might wobble chaotically, climates swinging to and fro over eons, challenging the persistence of complex life. And so, as we contemplate exoplanets in their billions, each with its own story, its own catalogue of conditions, we begin to see that the emergence of life is not merely a matter of orbit and sunlight. It is a tapestry woven from countless threads, the chemistry of air and stone, the warmth of the interior, the dance of magnetic fields, the legacy of impacts, the presence of oceans or deserts or ice, the stability of climate, the caprice of tides. Yet, even knowing this, we cannot help but wonder at the sheer abundance of worlds. In our galaxy alone, there are perhaps 100 billion stars, and it seems that most, if not all, are attended by planets. The census of Kepler and its kin suggests that small rocky planets in the habitable zone are not rare. There may be billions of Earth-like worlds scattered among the spiral arms, each with the potential, however slim, for life to arise. The diversity is staggering. Some exoplanets, like Kepler 186f, orbit quietly in the habitable zones of red dwarfs, their days perhaps spent in perpetual dusk. Others, like WASP 12b, are hot Jupiters, giant gaseous worlds so close to their stars that their atmospheres are stripped away, their skies glowing with the eerie light of vaporized metals. There are planets with days shorter than ours, and those whose years last centuries. Some are circled by rings more splendid than Saturn's, while others are attended by a retinue of moons, each a possible haven for life. We have found planets with atmospheres thick with hydrogen, and those whose clouds rain molten glass or iron. There are exoplanets with densities so low they would float in water, and others so compact their surface gravity is crushing. Each new discovery expands our sense of what is possible. The search for biosignatures, the chemical fingerprints of life, continues, ever more refined. Telescopes strain to catch a whiff of oxygen, a hint of methane, a subtle imbalance in atmospheric gases that might betray the presence of living metabolisms. But even here, caution is needed. Abiotic processes, too, can produce these gases. Volcanoes and photochemistry can mimic the breath of life. We must learn to distinguish the genuine from the false, to understand the context of each world, its history and peculiarities. In the end, the Goldilocks zone is a useful signpost, a first approximation in a universe of nuance. It reminds us that life as we know it depends on certain physical conditions, but it also challenges us to expand our vision, to consider the unexpected. Life may cling to the edges, to the deep oceans of icy moons, to the clouds of gas giants, or to the subsurface realms of rogue planets. The recipe of life is at once delicate and robust, shaped by the confluence of countless variables, some familiar, some wholly alien. As we drift further in this voyage, let your mind linger on the thought of those myriad worlds, each circling its distant sun, each bearing the imprint of its own history and chance. The next act will lead us deeper still into the chemistry that underpins the very possibility of life, into the strange and wondrous molecules that might bloom in the darkness, waiting for us to find them. The universe, in all its complexity, keeps its secrets close, but the story is far from finished. To seek out the unknown is a pursuit as old as humanity itself. For centuries the stars have gazed down upon us, their cold pinpricks scattered across the night sky, silent and mysterious. Our ancestors, huddled around the embers of ancient fires, peered upward and wondered, are we alone? Are there other worlds circling those distant suns, hidden by distances so immense that even the swiftest arrow would take eons to cross them? The urge to answer these questions, to decipher the cosmic ballet unfolding above us, has driven generations of astronomers, dreamers, and engineers, RS alike. In the earliest days, our tools were simple: our eyes, our patience, and our willingness to trust in the regularity of the heavens. The first astronomers, from Babylon to Alexandria, mapped the positions of the planets, noting their wandering paths against the backdrop of fixed stars. They traced the orbits of Jupiter and Saturn, observed Venus as both morning and evening star, but the idea that those pinpricks might harbor their own planets was too fragile, too revolutionary to be spoken aloud. Much later, as telescopes sprouted from the hands of Galileo and Huygens, the universe swelled in scope. Galileo, in the chill Venetian night, turned his crude lens to Jupiter and saw 4 small moons in orbit, worlds around a world, a miniature solar system. This discovery shattered the notion that Earth was the lone center of movement. Suddenly, the heavens seemed crowded with possibility, every star a candidate for its own retinue of invisible companions. Yet for centuries more, the stars remained mute. Even the most powerful telescopes showed them only as points of light, unmoved and unchanging. To imagine planets around other stars was an act of faith, not of measurement. The light from those distant suns, having travelled for years or centuries, arrived as a blinding wash, utterly overwhelming any feeble glimmer from orbiting worlds. For much of scientific history, the search for exoplanets was a quest for shadows, for hints and whispers that vanished under scrutiny. But the human mind is patient, and curiosity is a relentless companion. Astronomers devised clever ways to listen for the faintest clues, to read the starlight for the telltale signs of hidden worlds. They knew that while a planet may be too faint to see directly, its influence could still be felt, like a dancer tugging subtly on her partner's hand. An orbiting planet exerts a gravitational pull on its star, causing the star to wobble just a little as they both orbit their shared center of mass. This wobble, imperceptible to the eye, could, if measured with exquisite precision, reveal the presence of an entire unseen world. Thus was born the radial velocity method, sometimes called the Doppler wobble technique. Here, astronomers watched the spectrum of a star, splitting its light into a rainbow of colors. As the star moved toward Earth, the wavelengths shifted slightly toward blue. As it receded, they nudged toward red. By measuring these shifts, often just a few meters per second slower than a person walks, scientists could infer the gravitational tug of an orbiting planet. It was with this technique that in 1995, Michel Mayor and Didier Queloz made history. Using a modest telescope at the Observatoire de Haute-Provence in France, they detected the tiny oscillations of a star called 51 Pegasi. These oscillations betrayed the presence of a planet, roughly half the mass of Jupiter, orbiting astonishingly close, far closer than Mercury lies to our Sun. This hot Jupiter, as it came to be known, was unlike anything in our solar system. Its discovery electrified the scientific world. For the first time, a planet around a sun-like star, light years away, had left an unmistakable footprint. The radial velocity method, ingenious as it was, had its limitations. It was most sensitive to large planets orbiting close to their stars, the cosmic equivalents of heavyweight dancers circling tightly around their partners. Smaller or more distant worlds remained elusive, their gravitational whispers drowned out by the tumult of stellar activity. Yet the principle was sound, and as instrumentation improved, so too did our ability to detect subtler signals. Soon, dozens of exoplanets were catalogued, each one a new chapter in the story of cosmic discovery. But if the radial velocity method was akin to listening for the music of the dance, another technique sought to catch a fleeting glimpse of the dancers themselves. This was the transit method, a patient, statistical endeavor requiring long hours of uninterrupted vigilance. The idea was simple yet profound. If a planet's orbit happened to align just so, it would pass in front of its star from our vantage point, causing the star's light to dim ever so slightly for a few hours or minutes. Imagine the scene. A brilliant, distant sun, its light steady and unwavering, until, just for a moment, a small world glides across its face, blocking a tiny fraction of its radiance. For a star like the Sun, a planet the size of Jupiter might dim its light by about 1%, while an Earth-sized body would cause a dip of just 0.01%, a change so slight as to be almost unimaginable. To detect such a subtle event required not only precise instruments, but also luck. The alignment had to be perfect, and the observer had to be watching at just the right moment. For years, ground-based astronomers attempted to catch these transits, peering through the turbulent atmosphere, fighting clouds and moonlight. Progress was slow. The signals were dwarfed by the noise. The solution, as it so often is, lay in escaping the confines of Earth itself. And so, in 2009, humanity launched a watchful sentinel into the velvet darkness, the Kepler Space Telescope. Kepler was unlike any telescope before it, not a grand, swiveling eye scanning the heavens, but a quiet, steadfast observer, its gaze fixed on a single patch of sky near the constellation Cygnus. For 4 years, Kepler stared unblinking at over 150,000 stars, recording their brightness every 30 minutes, searching for the telltale dips of planetary transits. In its relentless patience, Kepler became a silent oracle. It saw the faintest flickers, the hush of a planet's passage, the regular heartbeat-like rhythm of transits repeating every few days, weeks, or months. From these patterns, astronomers could deduce not only the presence of a planet, but also its size, its orbital period, and, if combined with radial velocity data, even its mass and density. Kepler's harvest was astonishing. Thousands of candidate planets emerged from its data, a profusion of worlds, hot Jupiters, super-Earths, mini-Neptunes, and rocky planets, orbiting in the gentle warmth of their stars' habitable zones. Some orbited double stars, their sunlight waxing and waning as they danced between twin suns. Others circled faint red dwarfs, or wandered perilously close to the searing heat of their primaries. Each discovery was a testament to human ingenuity, a quiet triumph of mathematics and machine. But the story of exoplanet discovery did not end with Kepler. As the telescope aged, its reaction wheels, small gyroscopes that kept it steady, began to fail. Engineers, ever resourceful, repurposed Kepler for a new mission, K2, observing different swaths of sky and continuing the search. Meanwhile, other telescopes joined the cosmic vigil. The Transiting Exoplanet Survey satellite, TESS, launched in 2018, began scanning nearly the entire sky, looking for nearby planets suitable for detailed study. The transit method, elegant and powerful, revealed a surprising truth. Planets are everywhere. The Milky Way, it seemed, was a garden overflowing with worlds, far more diverse and numerous than anyone had dared imagine. Yet for all its bounty, the method was not without its challenges. Not every planet transits from our viewpoint. Not every dip in brightness is caused by a planet. Stellar flares, binary companions, and instrumental quirks can all masquerade as planetary signals. Disentangling the real from the illusory required careful analysis, tireless cross-checking, and often confirmation by other means. In parallel with these indirect methods, astronomers pursued the Holy Grail, the direct imaging of exoplanets. To do so was to attempt the near impossible, to glimpse within the blinding glare of a star the faint glow of a planet billions of times fainter. Innovative techniques arose, coronagraphs, which block out a star's light like an artificial eclipse, adaptive optics, which flex and contort mirrors in real time to counteract atmospheric turbulence, and, in the cold reaches of space, infrared eyes that could spot the residual heat of young, massive planets. Direct imaging has yielded only a handful of exoplanets so far, each one a precious jewel, often massive and still glowing from the heat of formation. In these images, planets appear as tiny dots, orbiting at vast distances from their stars, their light analyzed for hints of atmospheric composition, methane, water vapor, clouds of exotic minerals. The images are humble, but they are real, photons that began their journey on an alien world, crossing the interstellar void to touch a detector crafted by human hands. As the catalogue of exoplanets swelled, so too did our ambition to characterize them, to move from mere detection to understanding. Spectroscopy became our new window. By splitting the light from a transiting planet's atmosphere into its component colors, scientists could discern the fingerprints of molecules: sodium, potassium, perhaps water vapor, or carbon dioxide. These spectral signatures, faint and fleeting, offer the first clues about the nature of alien skies. Consider for a moment the audacity of this endeavor. To deduce the weather on a world light years away, to speculate about clouds of silicate rain or winds roaring at thousands of kilometers per hour. Each measurement, each spectral line is a note in the symphony of discovery, a testament to the subtlety and reach of human perception. The hunt for exoplanets has also inspired new forms of collaboration. Amateur astronomers, equipped with sensitive cameras and sturdy telescopes, contribute their own transit observations, confirming candidates and refining orbital parameters. Data from space telescopes is shared openly, sifted by algorithms and citizen scientists alike. The search for other worlds has become a democratic enterprise, a tapestry woven from countless acts of curiosity. Behind these achievements lies a deeper story, one of perseverance, of minds willing to labor for decades without guarantee of reward. The Kepler team, faced with budget cuts and technical setbacks, pressed on. Observers at mountaintop observatories braved bitter winds and sleepless nights. Engineers fashioned exquisitely stable spectrographs, cooled to cryogenic temperatures, to tease out the faintest signals. Each discovery is a monument to collective effort, to the stubborn refusal to be satisfied with ignorance. Even now, the techniques evolve. New missions, like the James Webb Space Telescope with its vast gold-plated mirror, promise to probe the atmospheres of Earth-sized planets, searching for the chemical whispers of life, oxygen, methane, perhaps something stranger. Ground-based arrays, spread across continents, synchronize their observations to detect the minute gravitational lensing events that can betray planets orbiting distant stars. The tools grow ever more subtle, the questions ever more profound. Yet for all our progress, the search is still young. The cosmic ballet unfolds, infinitely complex, forever just beyond our full comprehension. Each discovery is a step deeper into mystery, a new thread woven into the tapestry of the universe. The stars remain, as they always have, silent and watchful, their secrets revealed only to those patient enough to listen, ingenious enough to invent, and humble enough to wonder. As we look ahead, the horizon darkens with promise. New instruments, new methods, new minds enter the field, each seeking their own glimpse of the cosmic dance. What will they see, these future watchers of the sky? What worlds await, hidden in the glare, their stories written in the flicker of starlight? The quest continues, ever onward, as the night deepens and the universe whispers its endless invitation. Night lies deep over the earth, and in its velvet silence our thoughts are free to roam far beyond the bounds of our blue world. It is in such quietude that the mind becomes a gentle pond, still, reflective, and capable of holding the mirrored glow of distant stars. If you could drift at the edge of this pond, peering into its cosmic depths, the ripples would reveal not just the scattered pinpricks of light in our sky, but the grand tapestry of worlds that orbit them, the exoplanets distant and mysterious, each a bead upon the strand of the universe's imagination. To contemplate these worlds is to gaze into the pond and see not only our own face, but countless other possibilities shimmering there. Each exoplanet, some scorched and barren, others perhaps swaddled in clouds and oceans, forces upon us an ancient question, one that now grows ever more insistent. Are we alone, or does the universe teem with other watchers, also gazing skyward, also wondering? The discovery of exoplanets has not merely expanded our astronomical catalogue, it has transformed the very nature of our self-inquiry. For much of human history, the universe was imagined as a stage set for us, the central actors upon whom the spotlight must always fall. The stars were lights above, distant and cold, their purpose mysterious, but surely in some way related to our existence. The planets that wandered among them, Mercury, Venus, Mars, Jupiter, Saturn, were members of our own solar family, visible to the unaided eye, enigmatic but familiar. Then, in the latter part of the 20th century, the darkness between the stars began to yield its secrets. First with suspicion, then with growing certainty, astronomers found evidence that planets are not the rare jewels of a single solar system, but rather the pebbles strewn across every beach of the cosmic shore. The numbers are staggering, with hundreds of billions of stars in our galaxy alone, and with each star likely attended by its own retinue of planets, the tally of worlds swells into the trillions. The pond, once thought to hold only our own reflection, now reveals a multitude. But of these worlds, how many are truly like ours? Enter the Goldilocks zone, a poetic name for a concept both simple and profound. Not too hot, not too cold, but just right, the region around a star where a planet might sustain liquid water and perhaps, just perhaps, life. The Goldilocks zone is not a guarantee of habitability, but it is a necessary beginning. It invites us to imagine Earth not as a solitary miracle, but as one blossom in a garden of possibilities. Consider for a moment what this means. If planets in the Goldilocks zone are common, then the conditions for life, the right temperature, the presence of water, the gentle warmth of a sun, might also be widespread. Life, it would seem, could be the rule rather than the exception. And yet, as we peer into the pond, another possibility shimmers, that despite the abundance of worlds, life remains rare, a fragile flame flickering against the currents of chance. This tension between the apparent ubiquity of habitable planets and the unrelenting silence of the cosmos has been called the Fermi paradox. "Where is everybody?" asked Enrico Fermi, the Nobel laureate, over lunch one day. "If the galaxy is full of life, why do we not see it, or hear it, or find its traces among the stars?" The paradox is sharpened by our knowledge of the Goldilocks zone, for we now know that the ingredients are there, the oven is set to the right temperature, and yet the cake, it seems, is not forthcoming. There are many possible answers, each more evocative than the last. Perhaps life is indeed rare, a fluke of chemistry that occurs only under the most exacting conditions. Perhaps it arises often enough, but intelligent life, life capable of building radios, telescopes, and spaceships, is vanishingly uncommon, stifled by evolutionary hurdles or the perils of self-destruction. Or perhaps civilizations are simply separated by gulfs of time and space, too vast for messages to cross before the senders fall silent. Yet there is another, more humbling possibility, that we have not yet learned how to listen. Our instruments, advanced though they may be by the standards of our species, are still crude compared to the scale of the cosmos. If the universe is a pond, our ears are pressed to its surface, straining to detect the faintest ripple, the softest plop of a distant stone. The signals we seek may be lost in the noise, or encoded in forms we do not yet comprehend. These reflections lead to a subtle shift in our sense of self. Once, we saw ourselves as the center of creation, the singular focus of cosmic attention. Now we must grapple with the possibility that we are but one among countless forms of life, or else the lone voice in a silent realm. In either case, our significance is transformed. If life is common, then we are participants in a grand drama, sharing the stage with actors whose scripts we have yet to read. If life is rare, then our responsibility is all the greater, for to be the only witnesses to the universe's beauty is both a privilege and a duty. Philosophers have long pondered the implications of extraterrestrial life. Would its discovery upend our religions, our philosophies, our sense of meaning, or would it rather expand our horizon, deepening our awe and humility? Some imagine that the realization of cosmic company would be a balm to our loneliness, proof that the universe is not indifferent, but rather a place of fecundity and connection. Others fear that such knowledge would render humanity insignificant, a mere footnote in a story whose main characters dwell elsewhere. Yet perhaps these fears and hopes miss the point, for to seek life among the stars is not merely to look for neighbors, It is to deepen our understanding of life itself, its tenacity, its diversity, its capacity to flourish in environments both familiar and strange. Each exoplanet we discover, each Goldilocks world we imagine, is a hypothesis about what life can be. Some may harbour oceans beneath icy crusts, warmed by the tides of their giant planets. Others may possess atmospheres thick with ammonia, or rainstorms of methane, or clouds of glass that slice the wind at thousands of kilometers per hour. To stretch our minds across these possibilities is to exercise a kind of empathy, an ability to imagine forms of being utterly unlike our own. In doing so, we become more attuned not only to the universe, but to the fragile web of life that envelops our own planet. The search for exoplanets, for habitable zones, for signs of life, thus becomes an act of self-discovery, a way of glimpsing ourselves against the backdrop of infinite variety. Somewhere, perhaps, a civilization not unlike ours is pondering the same questions, their scientists and poets casting their eyes skyward, their thinkers drifting in reverie by their own cosmic pond. Perhaps they too have catalogued the planets of their star, mapped the habitable zone, wondered whether life might flourish in the warmth of another sun. It is a thought both comforting and profound. That curiosity, that longing for connection, might itself be a universal trait, written into the very fabric of living matter. There is a gentle irony in the fact that our growing knowledge of the universe, far from diminishing its mystery, only deepens it. Each answer opens new questions. Each discovery reveals new frontiers. The Goldilocks zone, once imagined as a narrow band of possibility, now seems but the beginning of a spectrum of habitats, each with its own peculiar balance of heat and cold, light and shadow, chemistry and chance. The more we learn, the more we are drawn onward, into the depths of the pond, into the heart of the mystery. And so, as the night deepens, we return to our own place in this vastness. We are the children of a small world, orbiting a mediocre star on the outskirts of an ordinary galaxy. Yet in the stillness of our cosmic pond, we have learned to ask questions that transcend our origins. We have learned to measure the faint wobbles of distant suns, to catch the fleeting dimming of starlight as planets pass before their faces, to sift the spectra of alien atmospheres for the chemical fingerprints of life. Each of these achievements is a note in the quiet symphony of our curiosity, a ripple upon the pond. What then would it mean to find life beyond Earth, to detect in the light of a distant planet the spectral signature of oxygen or methane or some other gas that whispers of biology, to receive, perhaps, a signal, a deliberate message crafted by minds other than our own? The implications defy easy summary. Some imagine a revolution in science and philosophy, a new Copernican shift that would reframe our understanding of life and intelligence. Others foresee a more gradual unfolding as the knowledge seeps into our culture, altering our myths, our aspirations, our sense of belonging. Yet in some sense we have already been changed. The very act of searching, the willingness to imagine life elsewhere, is itself transformative. It invites us to consider our planet as one among many, our species as a part of a larger community, whether actual or potential. This shift in perspective has practical consequences too. It sharpens our awareness of the rarity and fragility of our own biosphere, urging us to cherish and protect the only haven we know. In the play of reflections upon the cosmic pond, we see not only the universe, but ourselves, curious, fragile, capable of wonder. We are, at least for now, the universe's way of knowing itself, the eyes and ears and mind through which the cosmos becomes aware of its own grandeur. Whether we are alone or not, whether life is common or rare, this is a responsibility both daunting and beautiful. As the night wears on and the stars wheel overhead, we find ourselves drawn ever deeper into the mystery. The pond is vast, its depths unfathomable, its surface alive with possibility. Each exoplanet, each Goldilocks world, is a question posed to the darkness. Are you out there too? Are you watching, listening, wondering? Somewhere far away, a planet circles its sun, perhaps bathed in the gentle warmth that kindles, sees, and nurtures life. Or perhaps it is a frozen wasteland, or a scorched desert, or a world of storms and silence we cannot yet know. But the search continues, and with it the hope that one day a ripple will return across the waters, carrying with it an answer. In the meantime, we wait, we wonder, we watch. Our place in the universe is not fixed. It is a journey, a process of becoming. The cosmic pond stretches beyond sight, its possibilities endless, its mysteries inviting. With each new discovery, we cast another pebble, sending ripples ever outward into the unknown, into the night. As our journey through shimmering worlds and the gentle glow of the Goldilocks zone drifts to a close, may your thoughts float like stardust settling softly in the cosmic night. Rest easy beneath the vast whispering sky, and when your heart yearns for more Dreamtime tales, we'll be here, ready to explore the next mystery together.